we want to look at those ancient archosaurs. This is a Permian. Well, as it says, there are roots in the Permian. We start to see these creatures diversify. Remember, the Permian is when amniotes started to diversify as it became a drier climate, and archosaurs have their roots down there. So I've used this slide a bunch of times, cooler and drier. Here's our evolution. These are living amniotes, right? We're happy with this. So, dinosaurs are over here. Dinosaurs, these are the archosaurs. Dinosaurs in the strict sense are over here. So there's dinosaurs in there's a whole day between what I did an hour ago. Now there's dinosaurs in the toy sense, any ancient reptile-like things, a dinosaur. But, and that's those things here, ancient, large reptiles. Well, there's some here, they're over here in the archosaur. So in that lowercase d sense, dinosaurs are all over the place, but when we define them specifically, and then they're here on this tree here, all over the place. I'm getting ahead of myself. But when we define them specifically, they're over here. They're diapsid archosaurs. So, these are the dinosaurs here in color. These are ancient archosaurs. So, we want to see what's happening down here, and then what happened here that led to things we call dinosaurs? What was their origin? So, Archosauria is a name Koch gave us, 1869, and that includes the crocodilians, the dinosaurs, and the birds, and other cool stuff there. We're going to get to them not today, but eventually we'll get to Tyrannosaurus rex. Yeah, I've pictured Tyrannosaurus rex as fuzzy because they were almost certainly feathered. It's not how we picture them now. So, let's look at some of these fossil things that lead us towards dinosaurs. Here's an evolutionary tree. It's way too complicated for what I want to do, but it's in here for reference, and you can move your finger around it, but that's the big picture. They're way too complicated. Here's a much simpler one. So, I want us to get oriented on this. Did that. So here's the dinosaurs here. I highlighted them. That's where we're headed. But if we bring in our evolutionary tree for amniotes, remember? Birds and I turn this around, so don't get confused. Birds and crocodilians, they're over here with the archosaurs. And then stuff over here, there's still dinosaur-like things over here, but these are the lepidosaurs. This is the lizard snake tuatara crowd. That's over here. And the weird stuff, we don't know where it is, the question. So let's start at the bottom here. Let's work our way towards archosaurs. And there's just a funny few things to look at as we go along the way. There's a puzzling little group there. These are stem diapsids. That's the Permian stuff. That's those primitive early amniotes. The ranchosaurs. Ranchosaurs appear to be the outgroup, if you want to think of it that way, for archosaurs. They're the next thing down. They're funny little beaked creatures that are a Permian Triassic thing. And these distinctive beaks. And not unusual for almost everything we're talking about today is these were herbivores. Probably tearing into tubers or roots or maybe larger vegetation. But they're defining the base for us. So here they are. We're done with them. Here's the guy we're interested in. Who was the first archosaur? Founded this whole lineage there. What was going on down here? We have a group that's got quotes around it because it's an ill-defined group called thecodonts. And these guys diversified and were dominant in the Triassic. We don't have a lot of dinosaurs till after the Triassic, but these were basal archosaurs called thecodonts. Dont means teeth or tooth. Theco means edge. And their teeth are in sockets along the edge of their jaws. Teeth in sockets is another way to say that. Oh, there we go. There's a slide for it. There's a thecodont, and the teeth are in sockets. That's a new thing. We don't see that in more primitive creatures. They have these funny snouts on the end of their face, too. Look at those teeth. What kind of diet are we thinking now?
Carnivorous.
We're thinking a carnivore. Yeah, the rhinoceros appear to be herbivores, but we move into a carnivorous diet now. So what are these creatures? It's hard to say. There's a bunch of them, and it's probably a bunch of different things. Are they primitive archosaurs, or are pre-archosaurs? Are they primitive archosaurs? For our argument, it doesn't matter a whole lot. What they do for us is they set the stage for the archosaurs. They give us a point of reference for moving on. And by the way, look at the genus name here, Pterosuchus, primitive crocodile. Suchus, remember, means crocodile. So that's kind of, I drew this, that's kind of, it was early thought that they were, one nice discrete lineage, but it's not a monophyletic group, it's a bunch of different things, so we put quotes around it. And then here's the rest of the archosaurs, and that's where we're headed now. Here's the rest of the archosaurs, and thecodonts, well, however we want to look at them, they give us a good idea what that basal creature was. A elongate, kind of crocodile-y looking thing that was a carnivore and diversified into these different groups. So, what is an archosaur? We can get to creatures eventually that we say, okay, that's an archosaur. So who are these things? And there's a nice alligator to give us a point of reference. This guy. Oh, that arrow needs to go there. Sorry. Again, archosaur traits. We touched upon some of these earlier when we talked about defining the crocodiles. Archosaur traits. The skull has some very distinctive features. Among them, these two big fenestra or foramina. The one right before the eye called the antorbital, and one on the lower jaw called the mandibular. Now, these are unique features. What they do adaptationally, I don't know, but they define the archosaurs. The ancestor came up with that trait. I think we mentioned that one earlier. And we got and here's another one I don't think we've met earlier, and this is the femur. And the femur has this flange on it, this big bony ridge on it. It's called a trochanter, fourth trochanter. I'm not sure what that word means, but it's a very distinctive flange on the bone. Structures like that, when you look at it, okay, there's a hard structure. There's probably a function associated with that. And there it is on a dinosaur here, this feature here. When you see processes or flanges on bones, that suggests you something's connecting to it there. A tendon or a muscle is attaching there. And what we have in the beginning of the archosaurs, we've got a new muscle arrangement, the caudofemoralis longus muscle. Last time I'll say that word. It goes from the spinal cord, or the backbone, to that fourth trochanter. So that's a new muscle bone arrangement. What it does is it pulls the femur to the rear. A new kind of walking, a more efficient kind of walking. Something's going on in there. But that is an archosaur trait. And like I said, the teeth are in sockets. That may have evolved a little bit earlier. But that's a very impressive look at the weapons of this theropod dinosaur. And something really kind of nasty is the teeth are serrated. This is a dinosaur tooth. They got these little serrations on them. Thinking on the adaptive significance of that is it's not for cutting. They're not big or sharp for cutting. It's thought that when the animal ate something, food particles got trapped in those little grooves, and the food would sit there and rot. And so the next time they bit something, even if they didn't kill it, if they bit it and then it staggered away, it'd get infected and stagger away and die. That's why I said it's kind of a nasty food-getting adaptation. So, very complicated evolutionary tree. Here's our primitive archosaurs going up here, primitive archosaurs here, culminating in the crocodile crowd, and then going this way, you can see dinosaurs here. Oh, there it is simplified there. So there's the archosaurs, the thecodonts, confusing group, and the crocodilians. That's where we just defined these guys right here. Let's look at some of these primitive archosaurs. This is a Permian-Triassic group. They diversified widely in the Permian and the Triassic. And while earlier, particularly the creatures that are more closely tied to water, as those started to disappear in the arid Permian Triassic, these guys diversified, and they're a very, very successful group for that climate, that arid climate. And you can see these are all extinct things down here. There's the crocodiles up there. Crocodiles are survivors out of this group. And it was a pretty big array of creatures. A number of them are known from the fossil record. Like we talked about a few minutes ago, 23 surviving species out of this group. And there's this group right in here now, the crocodilia. Now, an important point here, and we've seen this in other groups we've met before, when this group originated and diversified and spread out into the habitat, it was a very broad, diverse group with a broad, diverse array of niches. These were some of the dominant terrestrial diapsids in the Permian and then into the Triassic. Into the Jurassic and Cretaceous later, they start to lose their niches to dinosaurs, and this stuff disappears. Remember how jawless fishes diversified enormously and then disappeared almost completely? I think it's a similar story here. And here's just some reconstructions or some skeletons here. Again, sucus tells you it's something that looks like an alligator or a crocodile. And there's a reconstruction of big goofy things. And skull reconstruction. So we're setting the stage here. The primitive archosaur is a carnivore with big teeth and probably fairly aggressive animals. Just again, keep thinking alligator. And we met him before. The Mesozoic crocodilians, they were all over the place. Some were aquatic, some were terrestrial. And Deinosuchus is this enormous one. That skull's been recovered. Oh, look, you can see the mandibular foramen right there. I don't know if I had this picture earlier or not. That's a Deinosuchus right there. And that's an American alligator skull right there. So these are fairly impressive animals. And I found these are all extinct things. Oh, no, this is the African crocodile. But all these things need to put crosses on it. These are extinct things. There's your person. So we're talking 10-meter long alligators in these Mesozoic wetlands. There you go. I like that picture. Okay. So, the early archosaurs, Permian, Triassic, and the Jurassic, they were diverse and abundant, diverse in all sorts of niches, all sorts of biologies. These, for at least through the Triassic, were dominant terrestrial diapsids. As dinosaurs diversify, the primitive body plan, the archosaur, loses sway, and dinosaurs dominate the Jurassic and the Cretaceous, and these guys start disappearing. And as they disappeared, they ended up in a niche that probably wasn't typical for the early ones. The later ones end up primarily in aquatic niches. They got pushed into that, kind of like jawless fishes got pushed into their weird niches. So that's a real late Cretaceous one. We're not used to seeing crocodiles walking upright, but that's probably what they were like. And by the time we get to modern times, we're pretty much looking at aquatic things. Wrong way. So that's the crocodilia, primitive archosaurs. And they have the archosaur's traits, and they're setting the stage for what's coming next. And what I think is just important to recognize, this creature in his highly specialized aquatic environment. But this creature, his basic anatomy, his biology, we're looking back to the Permian and the Triassic to this guy. Not that he hasn't changed evolutionarily since then, but that's a pretty neat peek into what those early archosaurs were like, the proto-dinosaurs. So my daughter looked at that alligator and said, that's a dinosaur. Not a bad guess. This was the last of the terrestrial crocodiles. Micosuchus inexpectatus. The last of the terrestrial members of this group. And it lived here in South Pacific on these islands, eating crabs. And it went extinct about 800-900 years ago. When humans started populating these islands, they hunted it or whatever, drove it to extinction. But that was existing in modern times. That's a real throwback to the Permian and Triassic, and we've lost it. So that's this stuff. We're good? I know it's a lot of names. Don't worry so much about the names, but the overall patterns. Let's move on and keep going. There's a big split in archosaur evolution right here. We're still not the dinosaurs yet. There's a big split. One huge group going this way, kind of maintaining the archosaur traditions, and a highly specialized group going this way. So a big split to dinosaurs and pterosaurs. And ptera is Greek word for what? Wing. Good, yeah. Wing or flying or sometimes fin. So the split gives us pterosaurs, and the split gives us dinosaurs. Let's go to pterosaurs. And again, all these cool paintings. There they are on our evolutionary tree. So this lineage went hyper-specialized towards flying, vertebrate flight. And we got flying in birds, but birds come much later. Here's an evolutionary tree. This will be on the test, I'm sure. Probably not. About 100 species are known, more than 100 species. It's pretty good for a fossil group, I think. They have the archosaur traits. These are good archosaurs. They've got archosaur skulls, the anterorbital fenestra, mandibular fenestra, this one's closed in. They've got the trochanter on the femur. They've got the serrated teeth. These are good archosaurs. They're just highly specialized. And I think it goes without saying, just like with birds, we see the basic vertebrate body plan highly jerked around and modified for flight. When you look at the anatomy, tremendous amount of that anatomy that's special about these things is about flying. The first one described scientifically was this guy, this Italian scientist, Collini, and he got a very good specimen. He looked at these limbs, and long, thin limbs, and he thought this was a thing that swam. He thought those were paddles, not wings. I'm not sure why. The ancestor of these guys, and we're going to hit this again, we're going to hit this kind of trend again when we look at birds, but the ancestor were probably smallish arboreal archosaurs of a type of animal we don't have today. We don't have a tree crocodile anymore. But back then, these were little small creatures probably jumping around in trees, and jumping around in trees is a jumping off point towards flying. We go from arboreal or tree living to walking around, maybe running and jumping, running fast and jumping, to gliding and flying. That's trend. We're going to not do it in detail here, but when we get to birds, I want to walk through this, not with these creatures, but walk through this transition going to birds, because birds went through a really interesting transition from walking to maybe climbing to running fast and to gliding to flying. So how does flying start? We see flying in all sorts of creatures today, and it probably starts with something like this. Gliding. You got an arboreal creature jumping and getting adaptations to catch some air, to get some lift. Not true flying as such, but that's the starting point. And that possibly is where it started for these pterosaurs. It's probably where it started for birds, too. We have reptiles today that do this. This is a Southeast Asian lizard that has big expanded rib cage, and it jumps out of trees and glides. It doesn't fly, it glides. And there's a fossil one from the Cretaceous. And you can see the ribs greatly extended out to create a gliding structure, shouldn't call it flying. So, probably where it started, these things were gliding, jumping off cliffs or jumping out of trees. And in the olden days, in the pre-dinosaur Renaissance, these were thought to be mostly gliders. They jumped off cliffs or dropped out of trees. They're probably sluggish, like we thought all these ancient creatures were. Modern ideas, again, they were possibly warm-blooded. Probably dynamic, active creatures, more like birds than like gliding lizards. And a lot of these hypotheses, again, we need time machines to test them rigorously. Classic one is pterodactyl. That's the one you hear that word pterodactyl, which means wing finger. Wing finger. And you can see about the size of medium-sized birds today. How large did they get? I like large and small, right? How big were these things? Quetzalcoatlus had a 13-meter wingspan. 13 meters. That's 40 feet. That's a big animal. Here's our scale drawing there. So there you go. How that thing got off the ground. That's pretty impressive. This is something so large, it might have had to jump off a cliff and start gliding. The niche for these things, a lot of them are thought to have a stork-like niche. They would walk, spend most of the time walking through vegetation like a stork does today, and grabbing prey out of the vegetation. That's big. They were pretty big. How small? Small is hard to determine because you might have a really small specimen as a fossil. It might just be a baby. Sometimes it's hard to say, but there are some fossils, but fairly small ones, and this is one right here. Mimicalopterus, that's the fossil, and that doesn't have scale on it. That's a reconstruction. So, songbird sized, as big as your hand. We can, again, look at structure and get ideas about the paleobiology of these creatures. Flight, for example, we understand how flying works with birds and with bats, with airplanes. We understand the physics of flying. We can look at their skeletons and understand how they worked. Flight's fairly simple. You need lift. You need thrust. Lift gets you up. Thrust moves you forward. Fighting both lift and thrust are drag and weight. And when lift overcomes weight and thrust overcomes drag, you fly. Same with an airplane or a bird. Here's the tool, the pterosaur tool. We have, well, I'll get that in a minute, but here's his hand. And this is the membrane, that's his flight surface. And look at this here. This is his ring finger. So if you look at it a little more, there's his hand right there, there's his arm. His ring finger is super long, and the membrane stretches off that. That's their solution to that problem of getting a wing. A lot of them walked around a lot. We have footprint tracks for them, and so the wing would be folded up with that big goofy finger tucked out of the way. The batteries are dying. There's just one more way to say the same as a skeleton. There we go, this slide I was looking for. There's a pterosaur, there's a bat, there's a bird. And that's three tools to do the same thing, to put vertebrates in the air flying. Bird wing, bat wing, pterosaur wing. It's all based on this structure, the three different ways to do it. Bats use the fingers. The membrane is stretched across the fingers. Bird, the feathers come off of highly modified wrist and hand. And in pterosaurs, it's that ring finger that does it. There's a bat, and there's his wing. You seen the bats on campus ever? When you're in the evening? We've got a couple. I've identified at least one little colony on a building across the street there, up in the under the tiles. There's a bird, which we'll get to next week, and highly modified forelimb, no fingers at all left. And then there's the pterosaur. So, 3 different animals, 3 different evolutionary pathways to flying. And we can look at this and then we can do physics on that. Once you reconstruct it, you can say, okay, here's how the physics impacts that. Here's the aerodynamics of that. And there's a tiny bit of aerodynamics. Question? Tiny bit of aerodynamics is nearly all the pterosaur wings we know of are what we call high aspect ratio wings. And that means they're longer than they're long and thin. And that's a very specific kind of wing. We see it like here on an albatross. That's a wing that gets a lot of lift, gets a lot of lift with very little input from flapping. It's a gliding wing. And it suggests that some of these pterosaurs, at least, this was what they were relying on. Once they're in the air, they're gliding. And there's a lot of diversity in birds. We'll look at this when we look at birds. There's a lot of diversity in bird wings. Pterosaur wings, not so much, it appears, but we're kind of limited on the fossils we have. Random things about pterosaurs. Their bones are hollow. If you're going to fly, weight reduction becomes important to you. And hollow bones reduce the weight. Where else do we see hollow bones? Invertebrates. Birds. We have them as mammals, but birds have them too. Birds go through some of the same weight. Birds evolve some of the same weight reduction mechanisms. There's evidence that they have air sacs, and here's something we'll talk about when we talk about birds. Birds have air sacs connected to their respiratory system throughout their body that lessen the density of the body itself. And there's evidence that when we look at the skeletal structure of pterosaurs, there's evidence of air sacs there too. Birds have a big bone on their sternum called a keel. The flight muscle's attached to it. If you don't fly, you don't have a keel. And pterosaurs have a keel. Birds and pterosaurs. So, same basic vertebrate body plan. We're starting with a vertebrate skeleton. Birds develop that skeleton into flight. Pterosaurs developed into flight. And they come up with some very similar adaptations. Air sacs, keeled sternum, hollow bones, things like that. You can look at the nervous system of a fossil. Well, you can't look directly at it, but you can look at the shape of the skull and the interior of the skull and get an idea what the brain was like. And pterosaur skulls, pterosaur brains, have enlarged optic centers. Vision's very important to them. It's very important for birds, too. The beaks were generally toothless, a lot, in some of them at least, which is another weight saver. Now, some are apparently fuzzy. This is not hair, because hair is a mammal trait, but it's a very similar to hair, just evolved separately. Think about that for a minute. Think about niche. Flying is energetically really expensive. You process a lot of energy to fly. That means your metabolism is high. Warm-blooded animals can have powerful metabolism. Warm-blooded animals can have a powerful metabolism. Cold-blooded animals have a problem with that. So the fuzzy fibers here may have been insulation to retain heat. These may have been warm-blooded or partially warm-blooded animals. The little fibers are called pycnofibers. That's not hair. They're almost certainly made of keratin. They probably looked a lot like hair, but they weren't hair. Hair is a mammal thing, but they're called pycnofibers. Birds are bipedal, right? Very few birds, matter of fact, if any birds use their front legs for anything but walk or flying. These guys were quadrupedal when they walked on the ground, and we have trackways for them. But that's probably what they spent a lot of their time doing, and I found this funny little cartoon of it. In a well-preserved fossil, we have evidence of what their mouth looked like. And we have a variety of different mouth constructions, just like we do in birds. And you can look at that mouth and go form, function, structure, niche. So this is one, I think from Argentina, if I remember correctly, Pterodastro, and has a very distinctive mouth arrangement there, and that's a reconstruction of it. Big long mouth, and it appears to have a bunch of fibers in it, or bristles. And that's one person's idea what that was about. He's filtering small invertebrates out of the water. Do you know a bird that does that today?
Flamingo.
Flamingo. Go to the zoo and watch flamingos feed. Their beak has these little filter elements in it, and they'll sift through the water for small invertebrates, and that may have been this niche here. This was a really small one, 5 centimeters, and it has a mouthful of small sharp teeth, not a long bill. Thought it'd been kind of a flying insectivore, like a swallow, or like a bat. The niche was there, bats weren't there yet, so the niche was open for anybody to use. A lot of them have these elaborate crests on their heads. Was it aerodynamic for flying, or maybe it was for display? And these might have been social animals. Birds are certainly social. These may have been social creatures as well. Those may have been for display. Look at this silly thing, Nyctosaurus. That's the skull, and look at this junk. This poor guy. Was it just a huge sail? Or maybe just a big display feature? We don't know, but that's pretty ridiculous. Very few small ones have been recovered, only a handful of eggs. There's a pterosaur egg. We don't know much about the early biology. And this is important. 2 vertebrates that fly. 2 archosaurs that fly. These are archosaurs. Birds are archosaurs. There is no relationship between the two other than they're both archosaurs. So there's that ancestral archosaur, and we have a branch that came off. That's the pterosaurs. And then later on, birds come off. Flying in birds and flying in pterosaurs are 2 completely separate evolutionary events. Pterosaurs did not lead to birds. As birds diversify, we'll talk about this later, as birds diversified, pterosaurs started to disappear. Is that competition? 2 flying archosaurs? Hard to say. But they're only distantly related, and any similarity they have that's about flying is coincidence. And what's the word we use that kind of evolution where different things acquire similar adaptations?
Convergent.
Convergence. Convergence, yeah. So they are extinct. They show up all the time. This is a faked photograph from the 1800s of a cowboy holding one. There's another faked photograph of some Civil War soldiers holding one up. And there's a consistent group of people. They're called cryptozoologists. And there's some cryptozoologists who are pretty sharp people, and they're finding interesting things. But then there's quacks, and there's a group of people who push really hard for the idea that pterosaurs are still alive, and we're just not looking hard enough for them. Their backstory is that they are young Earth creationists, and for some reason people think that if they find a living pterosaur or dinosaur, that disproves evolution. It doesn't, but that's their goal in life. When the coelacanths discover, say, oh, there's coelacanths, evolution didn't happen. So anyway. Okay. I'm getting tired. You guys are getting tired too. I'm going to call the day a little early. I'm going to go and work on the practical. So, Friday, yeah, you got the exams. Friday we got exam 2. I will go to my office. I promise not. Well, I don't promise not to forget. I will try really hard not to forget before I get there. Put up the review sheet for Friday's exam. I hope you've been reviewing for it. You don't have to know exactly what's on. Start reviewing. We'll do a little bit Friday, and we're not going to finish dinosaurs Friday, but we're going to start dinosaurs first thing Friday, take a few minutes, then you'll do your exam, and we'll probably finish dinosaurs on Monday, and then start birds next week. Okay? Can you believe we're halfway through? So, I'll see you over there around 1.
See it.
Oh, we do that.
As the internet time.
Yes.
Okay. Yeah.
Because they're going up there.
I'm gonna
Right
send
now.
order.
But,
I did microwave.
I need my phone on there.
yeah.
So when are we
Yeah,
gonna?
drop me an email or I'll bring it to
We usually
bring it to
start
the lab.
sensing here, but as soon as we
Okay.
just start it.
Thank you.